Welcome to our next lecture in the series on condensed matter theory. In this lecture I want to discuss the Hartree approximation. And Hartree originally introduced his approximation to understand the energy eigenstates of many electron atoms, but especially the extension, the Hartree-Fock approximation, can be used in a much more general fashion. And in this video I want to give you a physical understanding of how you can understand the Hartree approximation. And then in the next video I will have a look at a variational derivation of the Hartree approximation. And once we make that variational derivation, you can also see what the problem of the Hartree approximation is. And then see and understand why we have to have the Hartree-Fock approximation that corrects the problem that we have with the Hartree approximation. The Hartree approximation namely violates the Pauli principle. We can start with classical considerations if we want to derive the Hartree approximation. Classically, we can calculate the Coulomb interaction for two particles that are given by charge densities, rho A and rho B, at two different coordinates, or these can be delta functions if you have two particles really at some position. They can also be just some charge distributions. The Coulomb energy is always the same, 4 pi epsilon 0, or has the same form, and then the distance between the two particles. And as we do not talk about delta functions, but talk about distributions, we have to integrate over whole space, both in the coordinates r1 and in the coordinate r2. So that is the classical Coulomb interaction between two charge distributions. Now let's say that we have r1 particle orbitals, and these are eigenstates of the mean field Hamiltonian. Such that they describe our many-body wave function. Then we can define the charge density that we have in the Hartree approximation as a function of r, and it is the sum over all occupied orbitals and then the charge density that we have for each of the orbitals. I shortly stolpered because this is of course true at t is 0 for the ground state. We can also do this at finite temperature, where we have just a sum over all orbitals, then the Fermi-Dirac distribution at energy E, T and mu times the density that we have. This is the energy of the orbital that we have for that particular particle. And this is the valid approximation at any temperature. With this we can define our Hartree Hamiltonian as the kinetic energy plus 1 over 4 pi epsilon 0, and then the interaction between our nuclei, Ri minus Rj, the interaction between the electrons and the nuclei, and then the effective Hartree potential, which is our Coulomb energy. And if we want to have an integral over the expectation value of the ground state for the Hartree Hamiltonian to get the Coulomb energy, then we have to say this is a sum over all particles. We have the Hartree density at r e square over ri minus r. And we have then to integrate over the Hartree density. It is this later part in our Hamiltonian that then defines the effective potential that we have for our single electrons. And it is the eigenstates of this Hamiltonian, the one particle eigenstates, that define psi tau, such that h Hartree times psi of tau is equal to E tau times psi of tau. We now see that we have defined a Hamiltonian whose potential depends on the Hartree density, and the Hartree density depends on the eigenstates of that Hamiltonian. So we can start with some guess for our charge density. From that we find a Hamiltonian. From this Hamiltonian we find eigenstates, and these eigenstates then define a new charge density. That new charge density defines a Hamiltonian, that defines new eigenstates, that defines a new charge density, and you can iterate this until you find a self-consistent solution whereby the charge density defines a potential such that the eigenorbitals of that define the charge density that you started from. So you can iterate this to self-consistency. This is a procedure that we will encounter more often, that you iterate things to self-consistency and that Hamiltonians depend on solutions of that Hamiltonian when you want to define your mean field potentials. And we have here a potential that is basically just not considering the interactions between all particles explicitly, but took a classical approximation of that. So in the next video we will show that this derivation and procedure, although physically reasonable, is actually violating the Pauli principle by looking at a variational derivation of this Hartree Hamiltonian. And then in the video afterwards we will correct that in the Hartree-Fock approximation. Thank you very much for your attention. Stay healthy.